So today we're just going to do a quick overview of some of the engineering considerations when integrating the cells into a pack. So we'll talk about some of the required specifications, safety requirements, a few best practices, choosing the right BMS type, and we'll talk quickly about design for long-term manufacturability. When it comes to designing a battery for a particular application, it's important to understand the use case in the most detail possible. We usually begin this with the items detailed on this slide. It is important to consider the entirety of the use case when defining these specs. That use case up to and including the end user. So once we understand these key details, we then have what we need to select the appropriate cell. Once that cell selection is done, we then move to the required safety circuitry. All lithium-ion battery packs require protective circuitry of some sort. Specifically, those parallel cell groups must be monitored independently. Protecting via total pack voltage alone is insufficient. There are a minimum set of scenarios that protection circuitry needs to protect against. Those are over voltage, under voltage, overcurrent for both charge and discharge, and short circuit. In addition to that, there are often some regulatory requirements within the device specification that you need to meet. Those are often things like over temperature, under temperature, and redundant over voltage protection. There's two ways to implement that temperature protection, either within the BMS or by providing a temperature sensor for the target device to use. Both are totally viable. We usually start the mechanical considerations section by asking whether a battery is end user accessible or installed within a device in a way that can only be replaced by trained service personnel. If it's end user accessible, it really should be enclosed in some sort of rigid enclosure, usually something like injection molded plastic. If it's built into a device, you can usually get away with a soft pack with heat shrink. It's really just because removable batteries are inherently more vulnerable to being dropped or unintentionally abused. Dimensional requirements often end up driving much of the final battery solution. It's best to engage fairly early on in your design cycles so that the battery cavity dimensions are well understood. Some of the safety components within a battery can add up dimensionally a bit more than you might expect. IP ratings are also fairly important when it comes to designing the enclosure. Designing something that needs to be able to be submerged is quite a bit more complex than one that doesn't. Venting also becomes fairly important, particularly in the case of sealed enclosures. If there's some abnormal event that causes a cell to vent, there needs to be a mechanism for that pressure to exit the case in a safe manner. And next up, we'll talk about some measures to prevent thermal runaway. Some of these can be mechanical rather than electronic. So the easiest of them to implement is just spacing the cells further apart. This is also the most effective. So somewhere between 3 and 5 millimeters of air gap between the cells can pretty well prevent thermal propagation throughout the core. If that's not possible, then high temperature insulators or physical barriers can be placed between the cells. And cell orientation as well can be fairly helpful. Like you never want to point the vent of one cell at the side of another cell. And another fairly new mechanism we are seeing is submersion in phase change materials. The phase change materials are fairly interesting in that they're able to absorb quite a bit of thermal energy by changing from a solid to a liquid. The only consideration there is if you're going to implement one of these, the enclosure needs to be essentially waterproof since it will have liquid inside. All right, there's generally two types of BMSs, protection circuits and fuel gauges or smart batteries. The protection circuits are simpler, lower cost, and their protection functionality is implemented in analog hardware. So the result of this is you end up with fairly tight voltage tolerances and fairly reliable protection circuit as well. The only downside there is that changes to those thresholds require changes to the PCB or the BOM. Fuel gauges or smart batteries implement this with a combination of hardware and firmware. You can have multiple safety thresholds, both hardware and firmware, within a single part. And you will also get real-time communication, and it will tell you remaining capacity based on a impedance model of the cell. So those impedance tracking gauges are by far the most accurate, and they're able to monitor the state of health as the pack ages, kind of giving you a bit of insight into when to replace the battery. Another advantage there is that the changes to the protected thresholds can be done through configuration updates rather than hardware changes. And finally, a few points for long-term manufacturability. Really, the key one here is specifying alternates for critical components. If you can address this, you'll be in pretty good shape to keep supporting the product for whatever the expected life cycle is. And with that, I'm going to hand it back to Bob for some transportation and safety.
Thanks, Mike. Transportation in this case only covers lithium ion because of the safety concerns of lithium. There are lots of regulations involved that cover if you're trying to transport a lithium battery by air, sea, or land. But before we transport a battery, we have to put a lithium battery through UN 38.3 certification and testing. And this is a standard adapted by the world, by every country in the world, and it's mandatory for both cells and batteries. Lithium primary and lithium rechargeable are also required to be tested. So all cells used in a battery pack must have the test, and then the battery packs themselves should have a separate test. And this allows us to ship the batteries by any means anywhere in the world. And the whole purpose of this is to ensure that lithium cells and batteries are safe for transport. The tests consist of altitude simulation, thermal tests, vibration, shock, external short circuit, impact, over discharge, and forced discharge. At Excell Battery, we also have to worry about several battery standards, including the 38.3, but we also, if applicable, will look at UL 1642 and IEC 62133 that cover battery safety. Some applications require batteries and cells to follow these guidelines. Of course, we're also ISO 9001 and ISO 13485, but if you need a battery in HAZLOC, ATEX, or other explosive or place that requires an intrinsically safe battery, we have these other standards and regulations to look after when designing a battery.